Hi everyone. Today we're going to talk about section 11.2, which is volumes of prisms and cylinders. So volume is the space that a figure occupies, and it's always measured in cubic units. So the way that we mark that is, let's say we're talking about inches, we would write inches cubed. Okay. If they don't give you the units, you can just write units cubed. Volume should be something that you're probably familiar with. You've probably covered it in other classes a little bit. So today we're going to talk about some formulas that we can use for the volume of certain types of figures. Now, we've probably talked before about the volume of a box. So I'm going to go ahead and draw this little box here. Okay, this is one of the formulas, again, you might be familiar with. When we're looking for the volume of a box like this, you take the length, the width, and the height, and we just multiply them. So we do the length times the width, which is basically the area at the bottom, and we multiply it by the height. Okay, so hopefully that's a formula you've already seen before. Now, if we're looking at these two stacks of index cards, this first stack of index card pretty much looks like this box, right? So we've got the length, we've got the width is basically how far it goes. Let's see, it's kind of hard to mark on here. Let's just mark that part. And the height is dependent on how many index cards we have, right? Now we call this a right prism because it's basically perpendicular to the ground. It just makes this right angle. The stack is perfectly straight up, okay? Now, the next one is called an oblique prism. And you'll notice it's the same stack of index cards, it's just slanted over, okay? Now, if we're talking about the length, it's still going to be this side. Okay, the width is still how wide that index card is. But my height, okay, instead of going on a diagonal, height is always perpendicular. So it's just straight up and down, kind of like how it is here. Now, because we're talking about the same number of index cards, we just kind of slanted that over. Let's think about their volumes. So the first question here says, do you think that right and oblique cylinders have the same height? Okay, well, we basically saw that they did. If you're taking the same number of index cards and you're just slanting them to the side, the height will stay the same. And cross-sectional area. So cross-sectional area is going to be the area of one index card. Basically, if you were to cut through, what would be the area, which in this case would be length times width. Okay, now the cross-sectional area for this stack is also the same. So length times width. So we don't need to draw a diagram because we actually have our diagram up here. We're going to say that yes, they have the same volume. Okay, because if we think about our formula as being the cross-sectional area times the height, it's going to be the same for both figures. The cross-sectional area is the length times the width. The height is h, which actually matches our formula that we talked about earlier. Okay, that length times width times height, that's exactly what we have here. So it doesn't matter if you have a oblique prism or a right prism. If the dimensions are the same, that means you're going to have equal volumes. Okay, now we actually have another situation where volumes could be equal, and that comes from Cavalieri's principle, which tells us that if two three-dimensional figures have the same height and same cross-sectional area, at every level, then they have the same volume. So if you look at this first figure, and I'm going to highlight the cross-sectional area. Remember, cross-section is cutting a plane through a figure, so that flat surface has an area of B. Okay, so that's the area. If we had this different shaped figure, but it also had the same area, let's say this number was 20 and this number was 20, that would mean they would have the same cross-sectional area. Likewise over here, if this one is also B, well, as long as all these figures have the same height, then their volumes are equal, okay? Which leads us to question down at the bottom. Keisha's deciding between two canisters. Which canister holds more? What is the volume of the larger canister? Now, if you notice that the area, notice this is a jar that's straight up and down. This is a right figure. This one's oblique. Okay, notice it has the same height, but it's just slanted over. Now, if you look at the cross section of the area, let's say this 20 centimeters goes all the way through, right? So if I were to find the area of this circular top, okay, remember our formula is pi r squared. Well, the radius would be half of this, so that's 10, which leaves me with 100 pi. Now, in order for us to compare, so we've got 100 pi here, and notice it's 100 pi here. And notice that the heights are the same. This is also 25. Okay, that tells us that no matter what, your volumes are the same. Okay, and that's because the cross-sectional area or areas are the same and heights are the same. So that tells us that these two jars both have the same volume. Let's go ahead and flip to the next page. And here we have our formulas for the volume of a prism and the volume of a cylinder. So let's just talk about what a prism is first. So a prism has two bases and rectangular sides. We call those lateral faces. Okay, so in this particular case, notice that my base, I'm going to shade it in a little bit darker, so there's my base. The side that's parallel to that, the face that's parallel, is up top. So these are my two bases, okay? A cylinder is really similar to that. The only difference is that the bases, oh, and we should write parallel, two parallel bases, two parallel bases that are circles. Okay, so you'll notice that the base on bottom and the base on top, these are both circles and they are parallel to each other. Okay. Now, in order for us to find the volume formula is essentially the same. So it's basically the area of the base times the height. So the area of our base here would be length times width, and then we multiply it by the height. Okay. Now, the setup for the formula for a cylinder is pretty much the same. We take the area of the base and we times the height. Only thing is, area of the base for a circle is pi r squared, and then we multiply by the height. Okay, so once we plug the values in, it looks a little bit different. So let's take a look at our first example. Sarah needs to store 20 feet cubed of firewood. Could she use the storage rack shown? So we need to find the volume of this figure, and I gave you guys a hint saying determine the bases first. A lot of times students think the base is the bottom, but that's not the case here, because you'll notice if I look at the bottom of this figure, these two sides are not parallel to it. So really the parallel parts are the triangles. Basically the front and the back of this figure, okay? So here's the front, the back is behind it, you can't really see it. So the height is the distance between the bases. Which in this case are the triangles. So the distance between these is going to be the 2. That's my height. Okay. So I need to find the area of the base. And then we need to multiply it by the height. Now the base is a triangle. We know the formula for a triangle is 1/2 base times height. So I've got 6 times 4. This would be the area of the triangle. Now for volume, I need to multiply that by the height of the prism. So remember, the prism is the whole 3-dimensional figure. So the height of that is 2 feet. So this formula would give me the volume of my figure. Now if I type these into my calculator, I end up with 24 feet cubed. Now it says that she needs to store 20 feet cubed, and this thing holds 24, so we're going to say yes. Okay. Now we've got a couple problems down below. I'm going to have you guys pause the video, see if you can answer the following questions about volume. With number 5, you may need to draw a diagram, but I will work through that one together, okay? But go ahead and hit pause and try these next 2 problems. All right, let's check the answers for example 4. So plugging our values into the formula, we get 2500 pi, or if you had typed it into your calculator, that would be your decimal answer. Notice that both of these figures have the same base, okay, which is the same circular shape and the same height. So I didn't have to do the work twice. Each cylinder has the same volume. Now, if we were to double the diameter, that also doubles the radius, okay? So we end up with 10,000 pi, which notice that we quadrupled the volume. So doubling the radius actually quadrupled the volume of our figure, okay? Now let's do this next one together. So Catherine is using cans of juice to fill a cylindrical pitcher. So I'm going to go ahead and draw a cylinder, which I like to draw an oval on top, draw a line straight down, and then an oval on bottom. If you want to draw that back side dotted, that shows it's behind the figure. So it's 11 inches tall and 4 inches in diameter. Okay, so this is our cylindrical pitcher. Okay, now each can of juice is 6 inches tall. Just going to draw a can. So we've got 6 inches and a radius of 2. Now we need to see how many cans of juice are going to fit in this pitcher. So first we need to figure out the volume of the pitcher. How much is it going to hold? So we've got the area of the base, which is pi r squared, times the height. Typing this all into my calculator, so we've got 552.9 inches cubed is our volume. Now let's find the volume of the juice, or we'll say the can of juice. Pi r squared times the height. And we have 75.4. Now, in order for us to figure out how many cans of juice are going to fit into the pitcher, we would just divide these and say, okay, how many times does 75.4 go into 552.9? Okay, so we end up with 7.3. Okay, now obviously we can't use a part of a glass, so we need to decide, are we going to use 7 or are we going to use 8? Now, what would happen if we would pour 8 cans into here is that it would overflow, but we don't have to use the whole thing. So we could use 8 cans of juice. The problem with using 7 cans of juice is that we wouldn't fill it all the way, and we want this pitcher totally full, okay? All right, so let's go ahead and flip to our last page. Okay, now this last page has 3 more problems on here. Instead of me working through each one, basically we're using our formulas again. I will work out the solutions and post them as the scanned copy of the notes. If you have any questions, feel free to call in during office hours, either today or tomorrow, in order to go over this material. All right, guys, have a great day.